My name is Michael Schlitzer, and this is a review of my capstone project in data science at UMBC for spring 2021. My project was using machine learning and specifically neural networks to try and predict match outcomes from in-game performance indicators, or PI, in AFL games. Now, AFL is not American football. It's not this other game, sometimes called football. It's not rugby, and it's not Gaelic football. Instead, AFL, also known as Aussie rules or footy, is a unique game that is played on a cricket oval that's approximately 135 to 185 meters long and 110 to 155 meters wide. Like baseball fields in America, there are considerable differences between the dimensions of different ovals, and that in turn influences the way the game is played. Each team fields 18 players with 4 or 5 players on the bench, so there are 36 players on the field at any time, and each team announces its lineup, known as the 22, prior to game day. Unlike American football or rugby, footy is not built around oppositional lines. The game is fast and free-flowing, like soccer or ice hockey. You advance the ball by kicking it or hitting it by hand like an underhand volleyball serve, but never by throwing the ball. And you score by kicking the ball through the uprights at the end of the oval. There are actually 4 uprights. If you kick it between the 2 inner uprights, you score a goal worth 6 points. And if you kick it between one of the inner uprights and the outer uprights, then you've scored a behind, which is worth 1 point. If you hit either upright, then you default to the lower score, either 1 point or 0 points in the case of hitting the outer behind. So a typical AFL score is the number of goals followed by the number of behinds and the total. So you may see a score that says 10-5-65 plays 9-12-66. The background for my project was based on two papers that I read. They were really the springboards. The first, by Young, Luo, Gaston, Tran, and Dwyer out of Deakin University in Victoria, looked at similar in-game performance indicators, again, or PI, and found that the meters gained PI was the most important PI in predicting win-loss outcome of AFL games. And they primarily used the decision tree classifier to come to this conclusion. They set the high water mark for binary accuracy at 88.9%. The second paper, listed by Fahey, Gilmore, Peeling, and Rogalski out of the University of Western Australia in Perth, compared the performance of a wide range of machine learning classifiers on mostly categorical and biometric data. I combined their ideas rather liberally and to come up with my project. And so my research questions came down to this. Just from watching footy, I was skeptical of Young's findings. So my first research question was to see if the average meters gained PI could improve the predictive performance of the machine learning classifiers. My second research question, centered around the idea that breaking the team aggregate PI into position group PI might shed some additional light on how the teams are performing. So I wanted to know if this position group breakout could improve the predictive performance of the machine learning classifiers over that of the aggregate PI. Just a note about the 2020 season. As we all know, 2020 was a very interesting year. And if you haven't watched Making Their Mark on Amazon Prime, you should. It's a fascinating behind-the-scenes look at how AFL weathered COVID. But as a concession to the condensed season, AFL games were shortened by 20%. So to keep consistency across all the years in the sample, I multiplied all PI for 2020 by 1.25 to make the data comparable across the entire sample. So looking at the data itself, I used only publicly available data from a few key sources, namely afltables.com, footywire.com, and afl.com.au. I also consulted team websites and Wikipedia for player biographical and biometric data. And I wound up with quite a few data sets that then had to be merged together into one data frame for analysis. I started with data from 2012 to 2020. 2012 was the year that the current AFL took its shape with the addition of the Gold Coast Suns. But I was only able to find average meters gained data for as far back as 2015, so I essentially abandoned 2012, 13, and 14 from my analysis. This is what it looks like in AFL tables. You see all the players on the left side and all the PI for an individual game. I aggregated all that across each season. This is afl.com.au, a sample of the ladder, just the positioning of the teams at the end of each round. This is an example of average meters gained, I think, from footywire.com. And here's a CSV that I built of all the player names, teams, and position, and then biometric data. I combined all that into a data frame that looks like this, and you'll note there at the top there's D, and then PI, and then R and PI. In fact, there are 4 position groups I looked at: forwards, defenders, midfielders, and rucks. There are about 25 features per position group. So here's a couple housekeeping things. When a player was listed as playing multiple positions, I always assigned them to the first position listed. I did have to do some adjustments to the data for the ruck position for those few games where the ruck left the game due to injury. Most teams don't carry many rucks, so they would have another tall fill in for a round or two, and I dealt with that variance in my code, assigning the primary ruck PI, the hit out, to the ruck group, even if the player was a forward or a defender. All other PI remained with the primary position group assignment in those cases. So once I had all of the game data, I needed to combine it with the fixture data to compare performance in each round. So I created a home fixture and an away fixture that noted some categorical data like Fahey-Gilmore had, such as where the game was played, whether the game required interstate travel, whether the teams were playing in their home stadium or at a neutral site, etc. Then I subtracted the away PI from the home PI to get the relative performance across all PI, and that was the data that I used for the rest of the analysis. And this is what that looks like. So you can follow this. Course is looking at 2012. A negative number indicates that the away team performed better in that particular PI, and a positive number indicated that the home team performed better. Once I had this data all set together, I was able to create my experimental data sets. So again, I threw away 12, 13, and 14 seasons and restricted my analysis for my data set to 2015 to 2020. In samples 0 and 1, I re-aggregated the data. All that position group data was done away with, and I reconsolidated it back to the aggregate team level. So sample 0 was aggregate team level without average meters gained as a PI. Sample 1 then was the aggregate team level data with average meters gained. Samples 2 and 3, I reverted back to the position group breakout. In sample 2, there was no average meters gained for any position group, and in sample 3, the average meters gained was added back in. So this setup allowed me to test my research questions by comparing the performance of each classifier between samples 0 and 1 and 2 and 3, and also between samples 0 and 2 and 1 and 3. So now I start to get down to business, and here I took that data set and I used a label encoder to convert the target variable, the home win, home loss, to a numerical value of 1 or 0. Then I split the data into an 80-20 train test split, and I used a small sample from 2021 as an external validation set, which we'll return to at the very end. Now, looking at all of the PI, the range of the relative PI is very broad, so I needed to normalize the data. But I also wanted to exclude the categorical data from that normalization without losing the connection. And I was able to do that. I used the fit transform method to establish the fit on the test sample before using that model to then transform both the test and the validation samples for consistency. Just a brief final note in getting the data to this point. Of course, when you do a train test split, it leaves you with a NumPy array, which is kind of hard to look at and figure out what's happening. So my TensorFlow models use data frames, so I reconstituted the data frame and actually reconstituted the data frame along that train test split, basically just put headers back on, made it easier to read. But again, it's all based on that same, there's one 80-20 split for each data set across all of the machine learning models that I use from here on out. Now we get to machine learning, my favorite part of the project. Like Fahey Gilmore, I applied a bunch of machine learning classifiers to this problem. I applied 9 in total. And I really wanted to see if a tuned neural network could outperform the more straightforward machine learning classifiers. So I used 3 neural networks. A neural network built by Rauschka that does allow for backpropagation across the layers, a relatively simple TensorFlow sequential model, and a highly optimized TensorFlow sequential model that was tuned by Optuna. Now, outside of naive Bayes, each of the classifiers has hyperparameters to tune, and I did use a grid search and k-fold technique to tune each classifier to perform the best that it could on each sample. This really only had implications, as I understand it, for the statistical significance test at the end of the project, though. But I just want to, let you know that I did use k-fold cross-validation to tune the hyperparameters on these generalized linear models. One thing about those generalized linear models is that most of them are referred to as black boxes. You can't really see what's going on inside of the models. But the decision tree, random forest, and XGBoost classifiers do allow you to see which features are the most influential. So I took advantage of those models to see what was happening, to look in the window and see what was happening and compare my results on my data set to Young's findings. In my early exploratory data analysis, I had also run a t-test, and you can find kind of the results of that on my presentation for UMBC. And I was looking to understand the significance of the different features, so I had that as an additional point of reference. When I looked at all of the data across the aggregated and expanded data sets, I did not find that AMG was particularly important. It showed up in sample 1 as either the 9th or 10th most important PI, which is a pretty far cry from Young's findings as being the most important PI. In the expanded data set, 2 and 3 on the right-hand side of the screen here, no position group average meters gained PI even cracked the top 10. My data shows fairly consistently that kicks, marks inside 50, and inside 50s were the PI that ruled the day, right? Especially marks inside 50 for forwards, which makes sense since they're the guys that scored the most. Kicks, which is a measure of disposals, and then just inside 50s in general. They were across the board, across all classifiers, the most important PI. So I did not find that average meters gained was particularly important. One reason that I was really surprised by Young's findings was that just like in American football, it's possible to move the ball a lot. You can cover a lot of meters gained in essence, but not turn those meters gained into scoring opportunities. If you turn the ball over in footy, you can cover the middle part of the ground many times without really improving your chances of scoring, let alone winning. In American football, it's the equivalent of bogging down in the red zone. You can have all the yards you want between the 20s, but as long as the defense can stop you at the end, the yards really don't matter, unless you're just concerned for fantasy points. And I am not concerned for fantasy points. So turning to neural networks, the heart of my analysis, I started with Rauschka. And I really wanted to establish a baseline. And you can see that it performs pretty well, especially on the aggregated samples, 0 and 1 on the left side of the screen. It does not overtrain, and it minimizes loss fairly well. When we look at the expanded samples on the right-hand side, samples 2 and 3, we can see that the model still minimizes loss, albeit a bit more slowly, but it overtrains to the training set. You can see that in the upper right. There's a substantial gap between the accuracy of the training sample when compared to the test sample. Now, the Rauschka neural network does not lend itself to automated hyperparameter tuning. So it really creates a nice baseline standard for my neural networks, neural network models. It's kind of the naive Bayes of my neural network models. Next, I turned to TensorFlow, and I tried to improve on the performance of the Rauschka neural network. as you can see, my lightly tuned, it's tuned by my eyeballs, so to speak, my lightly tuned TensorFlow sequential model performed very much like the Rauschka model on the aggregated samples. It minimized loss fairly quickly, and it didn't really overtrain on the training sample or training set. But when I looked at the expanded samples, which of course had many more features, I found that it overtrained a little less in the Rauschka model, but it also had much more difficulty minimizing loss. I think that was due to the increased dimensionality of the data. If you look at sample 3, for example, it never did a good job of getting on track to minimize loss. And the problem with that, or the problem is that in order to overcome these obstacles, you have to tune the hyperparameters very finely. Normally, I would use a grid search to work through all of the possible combinations in a methodical manner. The problem, of course, is that the grid search is computationally costly, and that really translates to a time problem. The other problem is that the number of options inside of each hyperparameter makes grid search difficult to run. I had 10 hyperparameters that I wanted to tune, and some of the hyperparameters had up to 10 options. My first attempt at tuning the TensorFlow model with grid search meant that I chunked the hyperparameters and ran one or two at a time in isolation on the data set. I'd make adjustments and then I'd try to tune a few more hyperparameters. But this is not only inefficient, it also leads to wrong answers. The beauty of hyperparameter tuning is that they all need to work together. And if you have to artificially stop that or break it apart, you're never going to get the best possible outcome unless it's by luck. So Optuna really solved this problem for me. Optuna allows you to tune as many hyperparameters as you want in parallel, and it does it relatively quickly. You can maximize or minimize the performance of the tuner, and it basically compares the performance of the hyperparameter combinations and truncates those that perform poorly, narrowing in on the best performing combinations in a fraction of the time that grid search could do. So you can either maximize accuracy like I did, or you can choose to minimize loss, and the model can do either one of those things. Running on my laptop, grid search could run for hours, and it did, and it would return basically nothing, just never got anywhere, whereas Optuna returned an exceptionally good result in just minutes on each model. And as I said, I chose to maximize accuracy on the test data set in my Optuna models. Now, when I ran the Optuna tuner, these were the hyperparameter settings that produced the best results. You can look at these, and I can say with confidence that if I had to invent these numbers, these values, by guessing, this project would never have been finished. So Optuna was well worth the time that I took to learn it. You will note in this presentation that I am not trying to bore anyone with code. You can follow the link below to my GitHub repository, download and run the Capstone notebook, and take a look at the code for yourself if you like. At the end of the day, the question is, how did the classifiers perform? The results are framed by two lines. The bottom line, at around 70%, was identified by Fahey Gilmore as the tipping line, or generally how often the gamblers were right. The top line of 88.9% was the highest accuracy rate reported by Young et al. And you can see that in general, all of the models performed pretty well, with the exception of the decision tree models on the expanded data sets 2 and 3. None of the generalized linear classifiers were able to exceed the high watermark, but several of the neural network models were able to do so, and the Optuna neural network pushed 3/4 of the data sets over that threshold. To me, that's interesting. In this project, I wanted to apply neural networks to the problem, and I really hoped that they would perform well, so it was gratifying to see that they did. But interesting is not the benchmark. I addressed my research questions using McNemar's test for statistical significance. I used McNemar's test rather than the simple t-test because of the k-folds in my general linear models. Even though the train test splits were the same across all classifiers, the actual data that produced the optimized hyperparameters differed. I think that McNemar's test takes this variability into account and allows me to focus on the outcome of each classifier. So when I compared the performance of all classifiers on sample 0 to the performance on sample 1 to evaluate the value that adding AMG provided, I was unable to reject the null hypothesis. The smallest p-value for any classifier was 0.256, so adding average meters gained into the mix did not significantly improve the performance of any classifier. Then, looking at my second question, did breaking out the performance indicators by position group add any significant value? The answer was similarly definitive. Here I compared the performance of sample 0 to sample 2 and sample 1 to sample 3 for each classifier. The only classifier that showed a significant difference was the decision tree classifier, and that broke the wrong way, meaning that the aggregated data was significantly better than the position group breakout for that particular classifier. So again, I could not reject a null hypothesis, and the position group breakout was not only not as helpful as I hoped it would be, it was in fact detrimental to the overall model performance. So these two research questions are vertical analyses, meaning that we ask the question within each classifier. I also wanted to evaluate significance horizontally on one data sample across all of the classifiers. We've already noted that the performance range is fairly narrow, but when I applied that same McNemar's test horizontally, I found that a few classifiers did provide a statistically significant performance improvement over the others. As you might expect, the neural network models were all significantly better than the baseline naive Bayes classifier and the similarly poor performing decision tree classifiers. But the differences in performance between all the other classifiers, which are really in a 5–10% range, are not statistically significant. So I've provided this information mostly out of curiosity. As of the completion of this project, data from a few of the early rounds of the 2021 season was available to me, so I applied all of the same setup and normalization steps to that data and applied the fitted models for most of the classifiers to that data. The only one I didn't, I think, was Rauschka. And as you can see, the model still holds pretty well, and that encompasses changes to team composition from 2020 to 2021, and even a few rules changes. So it's good to see that the fundamentals of the model can withstand that level of variability and still perform fairly well. So in conclusion, this was an interesting project to work on. Getting the data into a format that could be analyzed, adding pieces in from different sources, that took a lot of time, and I learned a lot just from that process before even getting to machine learning. Then optimizing each classifier presented its own challenges, but each step was well worth it. To achieve a 90% plus accuracy rate on wins-losses using publicly available in-game performance indicator data is not a terrible outcome, not by any stretch. And my neural networks did outperform every other generalized linear model that I used. So I consider this project to have been successful. But I still think there is more to uncover here. There's more to do. I've been in communication with Champion Data, the official statistics provider for AFL, and hope to be able to get data that is even more finely tuned than my breakout, and begin to examine what success looks like for different position groups in different sections of the oval at different times in the game. I think that my singular focus on each performance indicator's impact on wins and losses may be a bit misguided, and I hope to be able to correct for that moving forward. That will require that I build a better neural network, and I think I'm up for the challenge. Thank you very much.